So everyone on Zoom, please mute yourself. Hey everyone, let's get it started. My name is Chip, run a Discord community with a horrible name but great people. So it's an MLOps learner, something. We never really came up with a name. So wait, I heard some echo of my own voice. So we are a pretty much a grassroots community. That means that we are very organized, very disorganized, but occasionally we come together to like create something really cool. So today we're gonna have a GPU optimization workshop. So GPUs are everywhere today, and learning how to use GPUs especially is one of the most important skills like nowadays. So when I was in college, a friend gave me a great advice. So he said that if you want to learn about something, just spend an hour talking to someone who knows a lot about the topic. So when I was learning about GPU optimization, I asked a lot of my friends, like, who are the best people that you know that I can talk to learn about GPU optimizations? And a lot of people that some of the like most of the people that my friends recommended are on the workshop today as speakers. So as for the workshop, I'm just going to give a quick overview. The workshop has 4 different talks. So the first talk is from Mark, who is a core PyTorch developer and also runs this really cool Discord server about specialized in GPU optimization, which called CUDA mode. So he's gonna give us a crash course on GPU optimizations. He believes that it would give us like a good fundamentals, like good foundations for us to understand the rest of the talk. But also because Mark is from if we're going on PyTorch, so the talk is a little bit PyTorch biased, which is not a bad thing because we're gonna see different perspective after as well. So the next talk is from Sharan from NVIDIA, talking about like surfing LLMs on GPUs using tool like TensorRT. And then after that, we also hear about Triton, which is also a very different GPU programming model, which is like block-based by Phil, who's leading Triton at OpenAI. And the last talk took a very different perspective. Like most people today are using GPUs for training and inference, but and so there's a huge category of workloads that GPUs are really good for, which is data processing. And William, who is a co-founder of Voltron Data, will be sharing that. So you can watch on YouTube, but also please feel free to ask question on Discord. It's just harder for me to like look at question discussion across different channels. So it would be a lot easier if everyone just like if we can all share our thought or feedback or questions on Discord, and we can try our best to respond to those questions. We also be having a share work note. The goal is that after the workshop, we want to create like summary key takeaways from each talk, and hopefully we can create like supporting materials for people who want to like dive deeper into GPU optimizations. Okay, so that's it. And let's welcome our first speaker, Mark Saroufim.
Thank you, Chip. Appreciate it. Here, let me share my screen. All right, looks good. Okay,
Yep.
sweet. Yeah, so I guess like Chip mentioned, I'm going to be giving a crash course on GPU optimization. The reason why I think this is kind of an important topic is namely because like GPUs are very expensive, and this has like a few important implications. Like they're expensive because a lot of people want them. They're also expensive because they're very useful. Like they make like a lot of models like significantly faster. And also like the demand is sort of like a bit unbounded, like as in if you get like twice as many GPUs, you might get like a model that's like better because of scaling laws. And so like there's always like going to be a room to make things like more efficient and faster. And so you could really, maybe an alternate title for this talk, it could be, how to get your money's worth like when you're buying a GPU. And so like at least like my perspective has been like so I'm a PyTorch developer at Meta. PyTorch is like a very popular programming language to like author machine learning models. I'm also the co-founder of a Discord community called CUDA mode where people are interested in ML systems and GPU optimization. And over the last like 3 months or so, I've been mostly spending a lot of my time thinking about like quantization, which is in the context of the AO repo here. So really the TLDR for this talk is like, I think there's kind of like 5 core techniques to make things go to make PyTorch models go faster. One is fusions, the other is like tensor cores, like overhead reduction, quantization, and custom kernels. So I'll just be giving you like a good crash course on each of these. The first thing is like if you go to the PyTorch GitHub page, the definition of the product, like what is PyTorch? Like PyTorch is a tensor computation language with strong GPU acceleration. This is sort of like really core to the value proposition of the library because like NumPy historically did not have like GPU support. And using GPUs within the context of PyTorch is actually quite easy. Essentially, you might like author like a specific program like the one here, where you instantiate different like tensors, like here we're doing this like with rand n, and then you multiply those two tensors with the torch.mm, and then you print the result. And as far as like a user is concerned here, interacting with GPUs is just like a .CUDA call. Uh, but the way this sort of works under the hood is PyTorch is a very general framework, and so it needs to work over multiple devices. So like, like namely like AMD GPUs, like Intel CPUs, AMD CPUs, like AMD GPUs, and a whole bunch of more exotic hardware over multiple D types. So like Torch Float 16, Float 32, BF16, and more. And then over multiple tensor layouts, like whether it's like sparse or different strided patterns. And so the reason why I'm going through this explanation is to really say that under the hood, you write your program in pure Python like this, but then there's like a whole complex machinery that will code generate the right kernels for your target device of D-type. As far as like why do people like PyTorch? I think the main reason why people like PyTorch is because you can add print statements. So basically, imagine that this is like a forward function, and you want to inspect the input x before like running a linear layer. Like in PyTorch, you can do this, and this is actually like quite non-trivial. And this programming model is called like an eager execution model. And what this means, sort of similar to Python, when you're running a PyTorch program, you will have like each line execute like one by one. So specifically, like let's say this like self.linear is making a certain call to the GPU, then it's going to basically make an asynchronous like call to the GPU and then like await like a result back and keep going. And for the most part, this worked perfectly fine for most of like the history of PyTorch. Uh, it has like a performance like implication in the sense that like you could imagine that instead of like running things line by line, you could wait to see what your full program might look like and do certain kinds of optimizations. But at least like historically, like when GPUs weren't like as fast as they are today, this wasn't like a huge deal. But the thing is, like the world changed, and the world changed in two major ways. The first one was the set of models that people started to care about has really converged, like around like specifically LLMs. And what this means is that like for a framework to be competitive, like performance really, really becomes like a very key value proposition. And this basically forces us to sort of like, and then the other thing is like GPUs got significantly faster. So doing this sort of eager execution model started to have like very, very serious performance implications. Um, so before we sort of dive into details, like this is like a really like important piece of background, and I want to describe like something that you'll hear a lot of people in ML systems talk about, which is an operation called a pointwise operation. So there's lots of pointwise operations that exist. Like one very famous one is the ReLU operation. And what the ReLU function does is it goes through every element of a tensor. And if the value is less than 0, then you just basically cap the value to 0 instead. So on the left-hand side here, you have like what the PyTorch code might look like, which is you instantiate a tensor, and then you call the ReLU function. And through like some pretty complicated machinery, you effectively will code generate something that looks closer to the right-hand side.
Wait, did we lose Mark or just me?
Yeah.
Oh, okay, let me speak with him. Hey everyone, while we're waiting for Mark to get back online, we are having discussions on the Discord channel. Um, yeah, okay, he's back. Yay.
I apologize. What was the last thing everyone heard? Like, which slide were we at? Can I share my screen too, please?
You just started
Yeah.
talking about point-wise ReLU.
Oh, sweet. Okay. Let me just share my screen again. Okay. Right. So here, like we have this function which is like the pointwise ReLU, and what the ReLU does is it applies essentially the max between 0 and the current element, and so effectively what it'll do is it'll just like remove all the negative elements and zero them out like in a vector. So on the left-hand side here, you can see like what like the PyTorch code would look like for this. And then on the right-hand side is kind of like a toy code generation example, which is like what a CUDA kernel for this might look like. And basically the important part is like on line 5. And on line 5, basically what we're doing is like we're basically checking if a certain like index value is greater than 0. And if it is, do nothing. And if it's less than 0, then set the value to 0. And the kind of interesting thing about like CUDA here is that like it's going to be launching like many like concurrent threads that are all going to be operating like over different like elements of this vector. So specifically here, as we're zooming into this kernel, we essentially assign every thread to like a location in memory. And one of the things that helps this kernel be a bit more performant is that like every thread, so basically thread index 1 holds memory location 1. And so if contiguous threads are holding contiguous points in memory, then the reads and writes tend to be like what we call coalesced, and this like improves performance. But for more complex kernels, like this term is often referred to as like a threading strategy, which is how do you assign threads to different memory locations, and this has like a dramatic implication on the performance of your kernels. So that's like one trick. The other really important trick is like taking advantage of the memory hierarchy. So you might have sort of seen figures around how like global memory is very slow. So for example, let's say you bought a 4090, like a 4090 has 24 gigs of VRAM. This is what's called global memory. And global memory is about like an order of magnitude slower than like the L1 cache or shared memory. Within CUDA specifically, you might instead like run this ReLU kernel by like loading your whole input into shared memory and then doing the ReLU operation within shared memory and then writing it back to global memory. But then there's other programming models, like for example, in Triton, you don't explicitly control shared memory and the sort of compiler figures out how to do this stuff intelligently for you. But really my point here is like between like the threading strategy and like thinking about like the memory hierarchy in GPUs is like a very core component to thinking about performance. All right, so let's go back to another pointwise operation. Another pointwise operation might be like a sinusoid operation. And so we're going to go over every element of a vector and like run a sign. But now we're not just running it once. We're going to be running the sign 4 times. So basically, the way this works is we're going to look at the input tensor, send it to the GPU, run the sign kernel, then we're going to send and then we're going to send like data back to the host. Then again, we're going to read another input tensor, and then we're going to send it back, and then again we're going to keep doing this back and forth. So this is kind of like the con of the eager execution model, is that you're basically doing a lot of like unnecessary data transfers to the GPU. And like basically, this is sort of like a similar kernel. So for example, this is a trace of like basically multiple cosine kernels, like one after the other. If you're using something like the PyTorch profiler, you can visually see this impact if you see lots of like very small bars here at the bottom in orange on your GPU side, and then these like chunky parts on the CPU. And this is generally like a sign that like, hey, you should be fusing more, and there's like a lot of overhead in this program. And the reason why like these memory transfers are really bad is because like this is, for example, like the data sheet for like an A100. And in red here, I have like the GPU memory bandwidth, which is essentially how quickly can we send data to the GPU. The GPU memory bandwidth is not increasing as quickly as like basically flops, as basically the speed at which we can do matmls. And so effectively data transfers is more often than not like the bottleneck in a lot of real world programs. So namely, So you might have also heard of this concept of like having kernels that are memory bandwidth bound versus compute bound. And I just want to give you like a simple formula for how to think about these problems. So again, back to our favorite pointwise op, or ReLU. Let's say we want to run this on the GPU. What does this look like? Well, let's say we have a vector. Every element is a float 32. Therefore, that means every element can be represented with 4 bytes. We need to read those 4 bytes. We need to run a single comparison operation, which is the max. And then we basically need to write back the result of the function. And that's another 4 bytes. We take the total number of ops and divide it by the data movement. So we get like 1/8. And if this ratio is smaller than 1, then that means we have a memory bandwidth bound problem. And the kind of like a very important problem you might care about is autoregressive decoding in LLMs is also a very memory bandwidth bound problem, especially at batch size 1. So this is not sort of like an artificial thing. Like memory bandwidth problems are like very, very dominant in ML. All right. So again, the idea here is like back to the sort of running the 4 sine kernels. Instead of running 4 sine kernels, can we just potentially run them all at once on the GPU and just send data out to the GPU just once? And this is kind of what motivated the creation of Torch Compile. So Torch Compile is what's called a fusion compiler. And so on the left-hand side, this is like the actual code to fuse this. I just like literally call Torch Compile on this like applying sine for times function. And what Torch Compile will do is it'll generate like a string representation it'll just code generate a Triton kernel for you. So we actually also have Phil here as the creator of Triton to talk to you more about how this would work. But if you run this program with this really nice environment variable called torch logs, and you set it equals to output code, you can like straight up generate all the Triton kernels. And basically everything here under the def Triton is the kernel. So because all of these writes are happening in temporary variables, we know that the kernel is being fused. And there's no concept of a thread index here anymore. Instead, Triton is sort of like it's like a less expressive language in the sense that you operate over blocks instead of threads. But that means like you don't have to worry as much about these details and have like the compiler worry about how to make this performant. I really love this trick. If you're learning Triton, I would say using Torch Compile is kind of one of the best ways to do it. Like look at this output code, change it. And if you're interested in how some of this machinery works under the hood, you can check out the PyTorch 2 paper below. All right. The other thing I want to talk about is like another part of the data sheet, which is basically the performance at like various D types. So basically you see here like at FP64, we're at 9 teraflops, but all of a sudden when we go to FP16, we're like at 300 teraflops. And so like just like orders of magnitude, like more improvements in perf. And so the idea is like, great, like, how can you use tensor cores more in your programs? Oh yeah, before I get there, like conceptually, tensor cores are like this special circuitry in NVIDIA hardware where it like breaks down large matrices into many matrices of size 4x4 and then like reassembles like the full result. These details like don't matter too much. It's more like if you're interested. However, like leveraging tensor cores within the context of PyTorch is quite simple. You basically just set this like this flag, like torch set float 32 maximal precision high, and you're going to be using tensor cores. So this is like usually the first thing I do whenever someone shows me like a slow PyTorch program. We've debated enabling this on by default. The only reason why it's not on by default is because this has like certain performance implications and will cause like accuracy issues. And unfortunately as well, there aren't like too many public docs about how tensor cores work. So I'm very glad we got to convince some folks at NVIDIA to come talk to us about like some of the tensor core internals on CUDA modes. And if you're interested, you can like register for this event. All right. So we've talked about fusions. We've talked about tensor cores. The third trick I want to talk about is overhead reduction. So remember the first example I gave you with PyTorch where we're running like a matmul, and then this matmul might need to run over multiple devices, D types, and layouts. And because there's like kind of like a high overhead to figure out like which kernel you might dispatch to, you end up having like most of your CPU time on your program just figuring out which kernel needs to be launched. And so, for example, here, this is like a flame graph from one of my colleagues' like blogs, like Horace, who has this like fantastic blog on GPU optimization called How to Make GPUs Go Burr. And he's showing here like a flame graph of like basically all the overhead that goes into when you're running a torch.add. So basically all of this is figuring out which kernel I should add. And then this like tiny little part here is the GPU kernel that's like running an add. So the main way of dealing with overhead on GPUs is basically you can think of like of CUDA kernels as being asynchronous. So basically you just send a kernel and then you await the result back. And so the key idea is that you want to queue up like multiple kernels, like one after the other, in what's called a CUDA graph. And historically, CUDA graphs were notoriously difficult to program with in PyTorch. But again, if you want to use them these days, you just need to, again, torch compile your model and give it like this other mode, which is called reduce overhead. We've also debated enabling this on by default. The only reason why it's not on by default is because CUDA graphs have a small memory overhead, which would make some models that were close to ooming all of a sudden but this is like a trait, like for example, I lean more on the let's just turn it on side of the debate, but this is why it's not on yet. Okay. The last trick I want to I have two more tricks. Like I also want to talk about quantization. So for example, here we'll notice, okay, well, we're going at FP16 and now like NVIDIA is also telling us like, hey, like you can also run like operations using like int8s. So this is really nice as well because like typically like a lot of deep neural networks, especially the linear layers, are not too sensitive to reducing the D-type. But like, and so this is an example of quantization that really helps for compute-bound workflows because we're just doubling the number of ops we can run. But quantization is also a very key optimization for memory-bound workloads. So again, let's go to our favorite function, the ReLU. So let's say now every element in the ReLU is an int8 instead of a float 32, which means that now, like instead of reading 4 bytes, we just need to read a single byte. We're still doing a single comparison operation. We're still writing a single a single byte, which means that the arithmetic intensity goes from being 1/8 to being half, and so this workload becomes a lot less memory bandwidth bound, and this is why. And this is really why like quantization is very popular like among like local LLM communities, especially at smaller batch sizes, because those workloads again tend to be very memory bandwidth bound. The other thing I want to talk about is like, so for example, this is a case study from work I was like really proud to be involved in, which was like GPT-fast. And basically in GPT-fast, we implemented what's called like weight-only quantization. And what this basically means is that while the weights are an int8, such that it makes the memory bandwidth pressure significantly smaller, the computation is actually still happening in BF16. So really to just run a linear, all you really need to do is like basically cast the weights and like run the matmul. So this brings me to sort of like a pet peeve, and I know like Chip always like likes to talk about my rant, so I figured I owed her like one quick rant, which is that like int8 is a very ambiguous term because it doesn't really tell you how, like in which D-type is the computation done. So the computation as in the activation. So typically it's int8 A16 is really what people mean when they say int8. But it also doesn't really tell you, are you quantizing the gradients? Are you quantizing the optimizer? Are you quantizing your KV cache? And so there's the D-type, and then there's the algorithm for how do you apply the D-type over like a real system. And yeah, like I said, it's not typically like a quantization is typically not applied to, for example, like reductions or normalizations. They're typically only applied to like the linear layers. And the other sort of like, this is maybe more bonus content. Like you might have seen, okay, people saying like, okay, we're going to run like bitnets, or we're going to run like in 2, or we're going to run like in 3, but like none of these have like actually support in PyTorch. So how does this actually work? So this is like, I don't expect you to read all of this. I just thought it was like a really cool trick. Basically, there's this old trick from systems community, which is called bit packing, which is assume you don't have a kernel to run int4, but you have a kernel to run int8. What you can basically do is you can like read the first part of you can split the int8 into 2 parts, and those are effectively int4s. And so by like packing them and unpacking them this way, it's actually quite easy to support like many smaller D-types and significantly reduce memory bandwidth pressure, but not increase basically the number of operations that you're doing, because you're actually doing more operations by packing and unpacking. So this is a brief fugue, so I don't want to go into this into a lot of detail. Right. So we've talked a lot about memory bandwidth bound problems, but what about compute bound problems? And unfortunately, compute bound problems require you to become better at math. And what I mean by this, like this is like a photo of Euclid to sort of inspire you here. And let me give you like an example of what I mean. So this is an open review from the Flash Attention 2 paper. And reviewer number 2 asked TreeDAO, why couldn't like a compiler come up with Flash Attention? And I should really like Tree's response here, which is that like compilers are generally great at performing fusions, but they're not great at rewriting your model, like rewriting the math of your model such that it's more efficient and still numerically stable. And so there's still very much a place for kernel authors to use like more compilers, so these two things are very much complementary. Like one doesn't like discard the other. So namely, back to like it's like a famous algorithm, like maybe the most famous CUDA kernel that's out like on the market today is Flash Attention. So Flash Attention has like a really nice like trick, which is one, it sort of takes a lot of advantage of like the memory hierarchy on the GPU, and so that's the figure on the left. But it also has like a very clever trick for how it computes like softmax such that you're reading less things when you're doing a normalization. And I don't think this was very well explained in the Flash Attention paper itself, but it was very well explained in another paper by Natalia Gimmelstein, who's a former colleague of mine at PyTorch and now again at OpenAI, where like this paper is called Online Softmax. And I really, really thought this was like this is very much like a paper that's like worth like 2 hours of your time. It'll give you really the core intuition behind Flash Attention. All right. Regardless, like, for compute-bound kernels, like I said, like the advice is not as actionable because it's really, go learn math, go learn CUDA. Learning CUDA isn't necessarily the easiest thing. It is very rewarding, but, learning CUDA these days, like just go buy this book. It's amazing. This is the book we use in the CUDA mode lectures. Do the exercises and, come to CUDA mode and ask us like questions about it. We actually have like two of the authors coming in and giving us like talks this summer. The other thing is that like you don't have to write CUDA kernels in isolation. And what I mean by this is that like typically when you're learning CUDA, you're bundling a bunch of complexity. You're learning CUDA, you're learning C++, you're learning about makefiles. But there's this really nice function in PyTorch called load inline, where you can pass it like a string to like a CUDA file, and then it'll automatically code generate like the right headers for you and the right like makefiles. And so this removes like two complicated factors from the equation, and it's kind of how I got started with like learning CUDA as well. The other tool of the trade is that like as you're writing like your toy kernels, NVIDIA has an amazing profiler called NCU, which will give you very actionable feedback, and it'll tell you, hey, like, this part of your kernel is not like memory coalesced, you should coalesce it more. And then you can give your whole kernel to ChatGPT and tell it, please, could you go coalesce this code? And it'll give you something. And I've like, again, found this to be like such an amazing supplement to reading the PMPP book. And I guess like once you're done with the PMPP book, like go write kernels. Like I would say like Triton sort of significantly lowers the barrier to entry. So we've aggregated a lot of interesting Triton content here in this repo. One sort of grievance I have is that like ChatGPT really sucks at Triton. And I think that's because there's not enough like Triton tokens that exist on the internet. So please help me create some more. If you're interested in like basically collaborating with others on real world kernels, like join CUDA mode. We have like Carpathy building like full training framework in raw CUDA. We have people building BitNet, people building FP6 kernels, ring attention kernels. So it's just really great to keep yourself accountable and meet peers. And once you're ready to ship your kernels, we have like many ways in PyTorch right now of basically making custom kernels be really seamless with user-defined kernels of Triton and custom ops. So if you're interested in shipping a kernel but don't want to deal with releasing it, like the release side of things, feel free to reach out to me. I'm especially looking at kernels that run well on consumer GPUs. So yeah, I mean, I'll sort of like end with these concluding thoughts, which is like, why should you bother writing CUDA and Triton kernels? I think like the real answer I have is like, it's fun, but there may be a more extrinsic one. And, a theme you should have for the rest of these talks is that it will never be the case that people will want slower models. So performance tends to be like a very defensible like career trajectory. And the last thing is that like a lot of online content on this stuff is really bad. And so all the good people I know have learned via mentorship. So that's why, I'm very passionate about like CUDA mode. So yeah, this was the summary of everything we talked about. You want to fuse things more, use storage compiled, you want to use tensor core, you set this env variable, you want to reduce overhead, use CUDA graphs, you want to quantize. This space is moving really fast. And if you want to write custom kernels, join CUDA mode and start writing more custom kernels with people. Personally, I feel like Torch Compile has solved a lot of my fusion, overhead, and tensor core problems for the most part. But one part where it obviously can't help me is around quantization and custom kernels. This is a space that's moving really, really fast. And it's why I've spent the better part of the last 4 months or so exclusively working on AO and on CUDA mode. So yeah, I would say I've aggregated a whole bunch of content here. So I'll make the slides available for people later. And I really hope you enjoyed the rest of the workshop and that this was kind of a decent crash course for you to really grok some of the more advanced content. And thank you so much, Chip, for inviting me.
Thank you, Mark. So I do have a question. So I think it's a great tutorial. It suggests people write kernels, right? But let's say let's say I have access to an open source model and I have access to some GPUs. What are some of the first steps I should follow, when I want to optimize? I don't imagine writing kernel should be the first step.
Yeah, so I would say it's actually roughly in this order that I've listed them out here. So the first 3 things won't take you more than 5 minutes to try out. It is in fact what I do anytime I see a slow model. And then I would say quantization and custom kernels are a bit more advanced, and so those require a bit more work. The problem with quantization is it has an accuracy implication, so you're running evals, whereas the first 3 are semantics preserving for the most part, so they are very easy to just switch on.
So another question we just saw is that how optimized is PyTorch on GPUs? Is there any low-hanging fruit or important optimization techniques that you feel PyTorch has not addressed?
Yeah, so I would say the main ones that are weak today are around quantization. It's very difficult to support sub-byte D-types in PyTorch for legacy reasons in the autograd system. So that's where I would say has been one of the main weaknesses of the library right now. And again, why I'm spending my time there myself.
Cool. So does anyone on Zoom want to ask questions? Feel free to raise your hands. Otherwise, I want to just ask questions from the audience.
I have a question. There's this new framework, Execute Torch, that is coming out. Does that help? And I mean, how is it different from Torch Compile?
Yeah. So let me maybe answer the first question first. So basically PyTorch has thousands of operations. It has a lot of ops. And those ops may or may not be supported on the sort of different kinds of exotic hardware people have on mobile devices. Typically those frameworks will sort of have only sort of have support for a much smaller set of ops. And so Executorch is really more it's more focused around that, which is how do you effectively run on these more constrained devices. And so things like power and size of the binary are way more important, whereas on server these are important but not critical considerations. However, there is an intersection, which is Torch Compile is actually split into 2 major subsystems. The first one is Dynamo, which basically captures a graph that you need to run, and then Inductor, which is what code generates Triton kernels for you. So effectively for mobile and these sort of on-device deployments, you'll capture a graph with Dynamo, but then the runtime will be Executorch, whereas on server the runtime will be Triton.
That makes it clear. Thank you very much.
Of course, yeah.
So Mark, we have other questions. So how does PyTorch treat other GPUs outside of NVIDIA GPUs? Okay.
Yeah, so I would say overall, I have a few answers to this. The first one is if you just say .CUDA calls in your PyTorch code, this will work perfectly fine on AMD devices. So that's great. The other thing is that this is, I would say, mostly thanks to the Triton team, is because they've essentially provided multiple backends that work on Intel GPUs, AMD GPUs. This makes things very convenient for us because if we just generate the same Triton kernel and this can run on any device, on any GPU device, that makes things really great. And so I would say overall, like this is like a space we're obviously like very interested in. And again, code genning is one, and code genning and sort of hierarchical IRs makes this a lot easier because we don't want to be in the business of rewriting all of PyTorch for AMD. Like that's just like strictly not a scalable approach, but code gen is. And so that's, I think, more the strategy.
Yeah, so another question is, what do you think about the 1-bit or quantization?
I think it's really cool. Like, I mean, like we have like a working group in CUDA mode that's like trying to do this. I think like the main challenge people are facing with like a lot of this work is that like they can't run evals scalably enough because like these models tend to be very slow. But I'm actually quite optimistic about like using Torch Compile to fuse bit packing. So we have like a lot of like interest in this in CUDA mode. We've already had a contributor do this kind of stuff for FP6. And I'm hoping to do this for like the int 1.5 work. So it's just very exciting. Like I would say like for a lot of these things, it needs more time to sort of really see which techniques will really pick up. But for sure, I think if you make kernels faster for people, you're going to just have more people experiment with these things. And so I'm personally spending time there. And if anyone in the audience is actually working with these smaller D types, just let me know. It's my day job.
This is awesome. And that's a question I want to ask on speakers is that what are some of the common pitfalls or mistakes you see people when they try to run things on GPUs?
So I'm gonna answer this in two parts. Like I think one is the eager part, and then one is the compile part. For compile, it's a bit easier. Like basically, if you're not enabling the first three things in this list, like I've seen many like advanced users even not do these things, and it was just kind of funny how bad the performance would get. I would say like for eager execution, I would say like optimizing the wrong thing has been like a very common theme I've been seeing where people like might pick up some like custom kernel, but like that kernel, like let's say total takes like 0.1% of the runtime of the program, but someone would go spend weeks on this. So that's why like I think like having this like profiling first approach to a lot of these things is very helpful. There's obviously like utilities like perf that give you a good macro overview, the PyTorch profiler within NVIDIA, NCU, and NSYS. So yeah, I would say probably that's the main one, is just not profiling and just optimizing things in an arbitrary way is the main mistake I see people making.
That is awesome. Thank you so much for the wonderful talk. We saw so many questions on YouTube and Discord. If you have time, we'll appreciate you answer the questions. Okay, so for the next speaker, we have Sharan Chetlur from NVIDIA. He is a principal engineer working on TensorRT-LLM team. He has been working on CUDA optimization since 2012, and he knows a lot about CUDA optimizations. So please welcome Sharan.
Thanks, Chip. Do you mind giving me a shared access? I lost it, I think.
Should work now.
All right. Hopefully you guys can see what I'm sharing. Sounds okay. All right. Hi. Thank you guys for giving me the opportunity to talk to you all. Thank you all for showing up. I'm going to be talking about high performance LLM serving on NVIDIA GPUs. I work on a product called TensorRT-LLM. The talk itself will be mostly about like conceptual things. I won't dwell too much on the product, but know that everything that I talk about is in the product. So I don't think it's much of an overstatement to say that LLM inference is one of the defining workloads of high performance computing today, right? There's an increasing need for deep learning in language applications, all kinds of language applications, chat, translation, summarization, search generation, very, very wide spectrum of users. Accuracy is really, really important, as you might imagine. It directly translates to how helpful the model is to the user, right? Which is basically the point of But all of these are also, they tend to be deployed in kind of an online environment or like in a data center environment. There are some use cases where it's done on edge, but most of them are, at least the ones that I'll be focusing on here are the ones that are done in servers and data centers that are kind of online systems. And so when you have an online system, or even an edge system for that matter, end user latencies are very, very important, right? Like, because people are interacting with these and you need to have a good experience doing that. But at the same time, multifunctional accurate models are large, making them really expensive to deploy. And if you're not careful about optimizing these in your deployment situations, you can land up paying a very, very high cost for running these services. So making a cost-effective deployment of LLMs is really challenging. The other side of this, which we're all seeing around us, right? Like it's just like an absolute proliferation of the kind of models that people are running. This has been true for all of deep learning, and it's also true for LLMs, right? Like where there's a very large ecosystem of LLMs being released, Llama, Falcon, Starcoder, all names that we're familiar with, many others. Not only are these architecturally different, they tend to run new and different operators. So these things are not static, right? Which is why Mark, who spoke for whom, he talks so much about things being customizable. Like being programmable is very important because people are changing what they want to do in all of these models all the time. And the third thing is that the latest models continue to be very large for the best accuracy. Models are just getting larger. That's just been the trend. There was about a year or so ago, a couple of years ago, when chinchilla scaling laws came out, and people were like, no, you don't need bigger models, you just need to train them for longer. Well, yes, but then if you make them bigger, they still get better. And so we're again seeing a trend of like models just getting bigger, tens to hundreds of billions of parameters or more for the biggest ones. Obviously, there are smaller ones that do well for other applications too. But in addition to being highly performant and robust, which is what you need to deploy, you also need the solution to be flexible or extensible, because what people want to run, production environments especially, is changing all the time. And that is why we built TensorRT-LLM, right? Like it's the goal of the library is to provide state-of-the-art performance for large language models for production deployments on NVIDIA GPUs. Like that's the whole. That's the absolute core of why TensorRT-LLM exists. In a rapidly evolving LLM ecosystem with models and techniques being released regularly, we need a performant and flexible solution to deploy models reliably. You can't hard bake things, and you also have to make sure it's like highly tuned, because otherwise you're going to be landing up with a very, very expensive solution. It doesn't actually give your users the kind of experience that they like. This presentation will focus on the performance side of everything that I said, not so much on the ease of use and flexibility things, though that's there, but that's part of another talk. But really, all the optimizations I'm going to be talking about today, they're in TensorRT-LLM, and they're essential to what it takes to serve a large language model in a production environment. So what will I talk about in this? At its absolute core, serving an LLM or any model, but certainly an LLM, it involves a forward pass of a neural network, right? And having that run really, really fast is the bedrock of how you make a whole LLM serving solution run fast. A lot of the techniques that were touched on previously, including fusions, eliminating overheads, all of that kind of go towards this bullet point about how do you make a single neural network run really, really fast. But in addition to running the forward pass of neural network efficiently, there's a lot of stuff that happens at the server layer outside that also has a profound effect on the observed latency and throughput. So intelligent batching of how you organize requests, how you batch things together, and how you lower them to the GPU makes a profound difference to request latency and throughput. And it changes how efficiently you use the GPU, because it changes the nature of the workload that's running on the GPU itself. And finally, I'll also talk about some modern techniques to improve GPU utilization and exploit properties of LLMs optimized for latency and throughput. Specifically, I'm going to touch upon paged KV cache use and speculative decoding. This is a lot of material, and each of these is like a universe in itself. So I apologize. This is going to have to be a pretty high level or quick talk, but I'm happy to follow up on any questions that ask for more detail on it. Okay, quantization. The essence of why, so bfloat 16 is the default data precision in the world of LLMs. Train models with bfloat 16, and the default is to kind of deploy it. But inference of these models can often be done with lower bit width precision, right? So on Hopper and future generations, there's 8-bit float, there's 8-bit int, there's 4-bit int, or even lower. And which parts of your network, whether it's the weights or the activations that you're actually quantizing, can also change. Like I said, there's a whole space here, and then Mark did a great job talking about this before me. But the short version of it is, as long as you can preserve accuracy, running lower bit widths is just an all-round win, however you quantify it. Whether you quantify it in terms of the latency or the responsiveness of your service, whether you quantify it in terms of like the throughput that you accomplish, the total cost of operation, across the board, it's just better to run lower bit width precision. It lowers the DRAM bandwidth pressure. It runs on a lower memory footprint, higher throughput communications between GPUs, because often you're serving these models across multiple GPUs, and how you communicate between them, it needs to be efficient. So higher throughput between them is important, and faster computation, right? Like you just your tensor cores run faster if you run with lower bit widths. How you there are, again, many ways to come up with a quantized version of a model. So you train your model in bfloat, and how do you achieve something that's lower precision that you can serve? Post-training quantization is probably, at least in deployment situations, the most common way to do this, but that it's by no means the only one. But the idea behind post-training quantization allows you to convert BF16 trained checkpoints into lower precision servable models. There's no additional training in that. There's no backpropagation and no updating of the weights, but you often need like some kind of a calibration step. And on the right, I have some speed up data indicate for some of these for Llama 3 models, showing how much faster things can get with when you drop your precision. I think data for 8-bit and 4-bit precisions. NVIDIA builds a software library that allows you to do this. It's called TensorRT Model Optimizer. It's available on GitHub. And there are several techniques that it offers. Post-training quantization is one of them. It's probably the most popular one, but it's not the only way to do it. There's also quantization-aware training, which allows you to, which requires you to retrain your model a little bit on a much smaller set of data. That can give you even better accuracy numbers. TensorRT Model Optimizer allows you to train with FP8, Int8, and Int4 today with advanced algorithms like Smooth Quant and AWQ. And there are some examples of quantization-aware training. We also do allow you to play around with sparsity. Don't think this is as much a mainstream technique for optimizing inference, but you can play around. And it has a lot of similar effects to quantization. It speeds up your math, reduces your DRAM bandwidth pressure, and your memory capacity. And it offers you some model optimizer has some pretty easy APIs to quantize whatever model you start off. So you can start off with your bfloat model, wherever you get it from, quantize it, and get going. On the right, I have some a table showing some accuracy numbers for how with things like FP8 and Int8, you actually on MMLU at least the accuracy loss is pretty small, and for most people it's acceptable. So if you can do quantize your models, it's worth making a little bit of an effort to do that, because for the most part, you can preserve your accuracy, at least when serving LLMs, and it makes everything run faster, cheaper. Awesome. Before I get into much more of the rest of the talk, I'm going to take a minute and talk about like the phases of an LLM request. Like, what does it look like computationally? There are two phases. There's a prefill phase and a generate phase. So what happens in the prefill phase is the user supplies the LLM a prompt or a query, and what comes out of it. So that's the figure of the bottom left, right? So you send in a prompt, and what comes out is the first generated token, right? Like first output token. But most of what it produces, it also produces this state that we call a KV cache, right? And the KV cache is it's a store of intermediate activations that are reused across your autoregressive generation steps. And think about it as like it's a pretty standard dynamic programming kind of trick where you store some of your intermediate values. So you're giving up some memory capacity, you're storing some intermediate values, and in exchange for giving up some of the memory capacity, you save a bunch of computations. You don't have to keep recomputing these values again and again. So the prefill state takes in a prompt, it produces your first output token, and it initializes this state that you're going to use to generate every successive output token. The generate phase starts from the previous state via this KV cache and the last generated token. So in this case, the gen token 1, and then it generates the next token, and it updates the KV cache for that. And so for every request, you call the prefill phase once, and then you call the generate phase in a loop as required to produce the full output. And why is this important? Well, both of these phases, they, from a computational standpoint, look very, very different. The prefill phase has a lot of parallelism because you can, for the most part, work on all of the prompt tokens in parallel, right? And so the operations, the matmulls, the attentions, everything, they tend to be, and the MLPs, they tend to be compute heavy, right? So they're more flops intensive, and they benefit very much from using tensor cores. But the generation phase tends to be much more memory bandwidth bound. There's just not a lot of parallelism. It's hard to fill the GPUs with it, and your limiter tends to be the DRAM bandwidth itself. The attention operation is more complex. Depending upon this situation, it kind of straddles the line between being computation bound and memory bound. Think of it like, if you implement it badly, it's going to be computation bound, right? Like you can very quickly land up spending all of your time doing flops. But if you implement it in a highly tuned fashion, which there are ways to do, so things like flash attention does this, it starts becoming more bound, which is great. TensorRT-LLM's fastest implementations used hand-tuned custom CUDA kernels for this. Flash attention, like it was. Flash attention, as described before, is a great reference. You guys can go take a look at how some of those are algorithmically constructed. After that, with any CUDA kernel, depending upon the problem size, you have to think about like how you parallelize the work and how you split it across all of your CUDA cores and keep them all busy. And that's a whole huge design space in itself. I'm not going to spend more time on it because I think that's a very, very advanced topic. And I'm going to focus on, I'm just going to state that we use our fastest kernels are handwritten CUDA. And I'm going to focus on how you actually work one level higher on top of this fast implementation of the forward prop of your network to do your LLM inference server really efficiently. I'm going to spend some time now talking about request scheduling and how this has a profound effect on how efficiently your LLM server can run. The traditional view of LLM inference treats a request as the atomic unit of scheduling. And if you've ever thought about how you run inference on something like a ResNet 50, this makes perfect sense, right? Requests are accumulated over some time window. So you have a server, it's waiting for requests that are arriving from different clients. You accumulate those requests over some time window, construct a batch of requests, and send it through your network all at once. I sometimes think of it as like the batch size view, where you have some number of requests, they're accepted, they run in lockstep all the way to completion, and are returned as a batch. This makes sense when one inference is one forward prop of your network, right? And that is a fixed amount of work that you have to do for every request. It's problematic when your completions differ massively in length, which is what happens with LLMs and just generative AI as a whole. So, for example, what I've shown on the left is 3 different requests. I've got prompt 0, 1, and 2 that all have very different lengths. So one is really long, one is kind of medium-sized, and one is short. And they all go into the LLM together. And what they produce on the output is also highly variable in length. So you can have really short outputs like, which is the tallest mountain on Earth? Well, Mount Everest. That's it. My answer's over. It's like, it's 2 words versus write me a story about something, and you can produce like paragraphs and paragraphs of text or even more, or generate some code. Like that can be really, really huge. There's simply no way to tell how much you're going to produce an output for a given request. You can cap it artificially, but fundamentally, there's no way to tell. If you imagine doing like the traditional static batching for this kind of network, you're going to see that the two, the purple and the yellow, the completion 0 and completion 1, they're going to have to wait for completion 2 to finish before the batch is done. And that means you get slowed down to the speed of the lowest work, of the slowest request in the batch. And that's miserable, right? On the one hand, if you're the person who issued prompt 1, like with this request 1, your completion was really tiny, but you had to wait the latency of the last guy to finish before you got your response back. So that's a crappy experience. If you're the person who's operating the service, you're paying all of these additional flops on like padding on nothing, right? Where you're leaving your GPU underutilized to do what it could have been doing actually useful things, and it's not. So what are some of the properties of LLM requests that need a new scheduling strategy? Well, GenAI inference iteratively invokes multiple forward passes per request. It's not one forward pass anymore. The number of passes is theoretically unbounded, right? In the most purest sense, you keep generating tokens until you produce some end signal, like an end of sequence or whatever. Practically, people put limitations on like what is the number of tokens you generate, but that's kind of an artificial thing. It's unbounded, and you don't know upfront how many tokens you're going to produce. Commonly, these LLMs are served in an online setting, so request arrival times are also known upfront. And the scheduler needs to support a changing workload because requests are ending and arriving all the time, and you have to be able to adapt to it dynamically, like over time. So what we implement in TRT-LLM, and this is not a unique idea, this is work built on many people, both in academia and in industry. We've done some great work. In-flight batching treats a single LLM iteration as the atomic unit of schedule. It's not a full request. All I'm treating is one LLM iteration. So what does this look like? So imagine this is a snapshot of your LLM server at the end of some iteration I, right? There are 3 requests that are relevant to this whole thing. There's request 0, 1, and 2. Just a note on the coloring, on the colors and the patterns. I'm using this hatched pattern to talk about like prompt tokens, so requests that have not been processed yet. They're just coming in. The solid dark color indicates tokens that have been generated already, and the solid light color is like if we had an oracle to say, hey, how much longer does request 0 have to go before it's done? We don't actually have this information, but it's just for illustration purposes. That's what this light color is showing. So if you look at what's happening in this system, you've got request 2 that's just come in. It's just a bunch of prompt tokens. It's not run through the LLM yet. Request 0 has produced some number of tokens, and it's got some way to go before it's done. And the last one, request 1, is a solid dark color. So it's produced all the tokens it's going to produce, and it's done, right? Like, so this is just a snapshot at the end of one iteration of the neural network. So what do you do now? You check for which active requests have met their end condition. So in this case, it's request number 1. That end condition could be maybe I produced an end of sequence token, maybe I hit the max number of tokens that the client requested, or I hit some kind of stop phrase, which is which is a way to program the machine to say that if I encounter this particular sequence of words, stop processing. Right? Whatever the condition whatever the reason for it may be, request 1 has hit its end condition. You identify that, you send the response back to whoever requested it, and you evict it from its active queue. This will go through no more processing. It's done as far as the LLM is concerned. At the same time, now you've got more space on the GPU available, right? Like you've got resources available because one of the requests that you were processing is done. You now get to admit newly arrived requests to accept the slot that was evicted by request 1. And so in the next iteration, so this becomes my new set of work that I have to process, go through one iteration. What happens in this iteration is everybody who's active advances by 1 stage. So request 0 produces 1 more additional token. And request 2, which was in the prompt processing stage, now goes through the prefill stage, which produces the KV cache and its first output token, which is what is shown. And now this is what the new system looks like. In the limit, if you do this perfectly, you should never have, nobody should ever overcompute. You should never have any padding of your output. And every request should get included as soon as it arrives. There's no time spent waiting in queues. Sorry, was there a question?
No, I think somebody just coughed.
Okay. Okay. And now everything that I talked about, why it's really important to a server, has nothing to do with GPUs at all until now. And why does this matter to GPUs itself? Well, transformer models usually consist of two kinds of ops, right? There's what we call token parallel ops, the things like matmulls and layer norms and things. They just operate on individual tokens, right? They don't care about where those tokens came from, whether they're part of a sequence, different members of the batch. They don't know or care. They're just, a token is a token for it, right? And then there are sequence parallel ops like multi-head attention or whatever attention mechanism you use that operate on a sequence of data, and they care very much about, which tokens belong in what order to which sequence. To a first order, unsurprisingly, given the size of the LLMs, the iteration time is dominated by the weight matrix multipliers, which are token parallel. So what if you notice what's happening in this picture is that in this iteration I, you now have some requests that are in their generation phase and some requests that are in their prefill phase, all coexisting. And this gives us the opportunity, because operators like matmul and layer norm are completely token parallel, what you can do is you can simply concatenate all of those tokens. Well, that's kind of what I've shown in this figure. So within the LLM, we've got in this cartoon 2 requests that are active, one of which is in the generate phase, the other one which is in the prompt phase, and I can just simply take those prompt tokens and concatenate it with the one generate token, which is all the gen phase needs, and I can run that through my network all in parallel. And what this does is, instead of being in the memory bound region, because you are only in the generation phase where you're only operating on one token at a time, you've got a whole lot more parallelism available in this situation, and the machine as a whole in this iteration can run at a much higher efficiency, right? And so what our in-flight batching technique has allowed us to do is redefine the workload that's running on the GPU, and that improves the overall efficiency, the throughput that you're running. The other optimization I wanted to talk about is this idea of the paged KV cache. The KV cache in general grows with the sequencing, and traditionally KV caches were viewed as contiguous regions of memory. This leads to a simpler implementation of the attention. So if you just look at what I'm showing on the bottom left figure, the contiguous KV cache, each row in this represents a request. Again, as in the previous example, the solid dark color indicates tokens that are actively, those are regions of memory that are actively in use. So they were produced by either the prompt tokens or actively generated tokens. The light solid regions talks about again, if you had an oracle to look into the future, at some point, those will be filled during the lifetime of the request. And the gray stuff is all unused memory. And as you can see, because you need to pre-allocate memory based on what you think is going to be like your worst case sequence length, it often leads to a lot of wasted stuff, which is this gray region, right? Like that memory is never going to be used, but you've reserved it up front and it's wasted. And why is this important? It's because very often the memory capacity is a limiter for how much you can run, like how much parallel work you can run on the GPU at once. And so paged KV caches kind of reimagine this. They say instead of having the KV cache be just one continuously growing buffer in memory, we're going to think about it as like a linked list of pages, right? And so this page that I've shown here is, let's say it'd be something like 32 tokens or 64 tokens, something very small. But now if I have to reconstruct the KV cache for, let's say, this magenta token, I now have to follow this linked list of pointers that tells me, hey, here are all the blocks that you need to traverse in order to reconstruct your KV cache. And the reason this is important is twofold. First, the amount of allocated but unused memories is minimal. It's at most your block size -1. So there's much less kind of unused memory. And second, all of this gray stuff, it's not reserved, right? Like even if you don't use it for a certain request, it's available for other requests to use. And so you have this lazy memory allocation scheme where requests keep allocating pages as they grow, and the whole pool of memory is available, so that you can naturally adapt to having. You can have a large number of small length requests, or you can have a small number of very large length requests. It adds a little bit more complexity to the attention kernel and costs a little bit of efficiency, but overall it makes the GPU itself run in a much more efficient way, because you can have many more requests in flight because you're no longer bounded by your memory capacity limitations, which were because of all of this wasted space in the contiguous game. And now there's an even more interesting optimization that you can think of, right? Like, which is once your KV cache is no longer contiguous, it's just a bunch of chunks in memory, and you have a linked list, you're chasing pointers to reconstruct your KV cache. It allows different requests to share physically the same regions of memory. So for example, I'm showing here the example of a system prompt. So for those who are unfamiliar, the system prompt is kind of like rules of the road, some boilerplate that's appended to prepended to every request that comes into the system. So something like, you're a succinct and helpful bot, your name is blah, 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 you must follow the user's requirements carefully and to the letter. And you can imagine like this can get really long, and you can also see how this is very important to the LLM producing useful responses, right? But this is boilerplate. This is shared for every request that comes in, and it's just prepended. And so instead of materializing this redundantly for every request, because you can now do this pointer chasing, you can map it to the same physical regions in memory and just have your pointers point to those regions to reconstruct your sentence. And as you can imagine, this saves memory even more, right? Because you're avoiding all of this duplication. And it makes things even better, because when another request comes in, instead of recalculating these blocks, you can say, hey, I can just refer to stuff that was already present in memory. It also saves a bunch of math, reducing your overall runtime. And then just one last topic I wanted to touch on was this notion of speculative decoding. It's a really powerful class of techniques. Again, it's not one thing. There's many ideas about how to do this. And it hinges on the observation that at low batch sizes, the generation phase significantly underutilizes GPU resources. So your regular autoregressive generation is given a sequence of tokens, 0 to n-1. Can I generate the nth token, right? Like that's what autoregressive generation does. But what speculative decoding says, well, suppose we had a way to guess tokens n+1, and n+2. I'm using 3 as an example. It can be any number, right? It takes approximately 0 additional time to also check if n+1, and n+2 are the valid next 3 tokens of a sequence. So what this looks like is you start off with a set of n minus, in this case, n tokens 0 to n-1, and your standard autoregressive generation generates the nth token of the sequence, which you will do anyway. But it costs almost nothing in the same time to also evaluate if these draft tokens are valid. And if they are, then what that allows you to do is advance the state of your generation by more than one request, which statistically leads to much lower latencies. I know I'm out of time, so I'm going to stop talking this almost at the end of my presentation. Chip, happy to take questions.
Thank you. So we have like a lot of questions on YouTube and Discord. So for the speculative decoding, how feasible or how common do you see it going to be used in the future?
Oh, I think it's going to be very, very common everywhere, because especially as models become larger, the responsiveness, the latency is going to matter more and more. And this is, and so you can't run a very large number of requests at once. The beauty of speculative decoding is that it turns a latency problem into a throughput problem, which is great for GPUs, right? And so traditionally optimizing for low latency scenarios on GPUs is hard, but with speculative decoding, you can turn that into a throughput problem, which GPUs are great at. And so I think it's in the future, it's going to be a really important way to balance lower latency with cost.
And can people just do it like out of the box, or does it have to be very like model dependent?
There is some model dependency on it, and there's a design space around how you come up with your draft tokens. So some of the ways in which people can do it is you can have a smaller language model, doesn't even have to be an LLM, that proposes these draft tokens, and sometimes you can get a pretty good hit rate with that. You can also rely on your cached history, which needs no additional work, no additional changes to your model, or you can modify the model architecture. So there's techniques like Medusa to produce your draft tokens along with your forward problem and do it all together.
So on the slides, you also mentioned you made distinct differences between time to first token and time between token. So for you, like which is harder to optimize for?
Usually it's the time between tokens, because the generate phase being memory bound is much harder to optimize for. The time to first token, it can be a problem if you have, I apologize, I'm just going to go back. So the time to first token can be a problem if you have a like really, really giant prompt, but usually crunching through a lot of math is what GPUs are great at. DRAM bound workloads are much harder to make faster because just the memory technology is not keeping up with how fast computers is getting faster.
Yeah, and I hope that speculative decoding will help with this. So
Exactly.
yeah, so I understand that you're serving, right? There are multiple mode of serving, so like online and batch. How common is each mode? Like, what's the demand for like online inference versus batch inference that you have seen?
Almost everything is online is far more important. But the whole purpose of things like in-flight batching is you turn an online serving problem into a batching problem with sufficient flexibility in the underlying hardware. And so that's how you balance actually using getting the efficiency benefits of batching while also maintaining good latency and responsiveness.
So what like so you're saying it's like online inference is like way more important, but people have like you are actually trying to batch requests as they come in online, so like you can still get higher throughput with like
Yes.
minimizing the latency.
That's right.
Oh, that is very cool, because I saw like something like OpenAI for the batch mode is just like 50% off like per token, something like that.
Sorry,
So,
I don't know enough to comment.
yeah, so if anyone has questions on Zoom call, feel free to jump in. Otherwise, I want to continue asking questions from the audience. So I think it's like one thing I think that one common mode we use is like the streaming mode for like to generate tokens stream by stream. Or sorry, token by token. So is there any like specialized optimization technique we have to do to like optimize for streaming mode?
Not really. So what all that happens is, if I can just go back to this slide, right? Like the only thing that changes in streaming mode is that now instead of waiting for the response to be complete, you also stream out tokens at the end of every iteration. So you do this with the in-flight batching. You're assessing the state of the world at the end of every iteration, and all you're saying is, even if the request is not complete, I'm going to stream out whatever token you produced last time around. And all of this is usually done asynchronously. It makes almost no difference to the GPU.
Oh, this is cool. Yeah, so I think like people like so you also like emphasize the importance of quantizations, and it sounds like a free lunch. Like everyone should just do it. Like, are there any drawbacks to like post-training quantization?
Yeah, I mean, you have to do it carefully. So you need something like, well, okay, first of all, post-training quantization, this is absolutely model dependent, right? Like what kind of accuracy drop or not you see is very much dependent upon your model and your use case, and also upon your appetite. Like even if there is a little bit of an accuracy drop, maybe you're okay with it because it's so much cheaper and faster to serve a quantized model. So yeah, you definitely want to be careful about like that trade-off between how much accuracy loss you're willing to tolerate versus the performance benefits. And also, for sure, like, simply downcasting and converting, that's not going to work at all. So you need to have some kind of, even if it's not necessarily a library that somebody else has written in, these techniques are well documented for how you calculate the scaling factors appropriately and make sure your post-training quantization, your quantized model still maintains accuracy. I'm sorry, Chip, you're muted. I can't hear you.
I was going to say Chip's on mute, so I'm going to go ahead
Oh.
and jump in front because she's busy. One of your techniques that you mentioned, I'm just blanking on the name, but one of the techniques you mentioned was basically redefining the workload method.
Yes.
What was the name? And you mentioned that this is like standing on the backs of other academics. So like, is there like a good introductory paper that starts to kind of talk about this technique that you could recommend?
Yeah, there's let me leave a link in the Discord. Like there's a paper called Orca, which is a good one to look at. And there are others also. So let me leave a link in the Discord if that's okay.
Yeah, that's fine. I'll keep an eye out. Thanks.
Thank you.
Also, yeah, sorry, we just saw I was on mute earlier. So there's another question from the audience. Like, do you have any advice on how to go about choosing an inference service? Because there are like many of those out there.
Use TRT-LLM. Why would you need anything else? No, I'm sorry. I'm joking a little bit. I think depending upon what your goals are, like all of them are optimized for slightly different parts of the problem space, right? Not everybody needs the absolute last drop of performance. I understand that, respect that. Some people just need things that are more approachable. There are a number of options available, and they're all very good, and you kind of have to explore them a little bit for yourself. Like especially if what you're looking for is an on-ramp, there are some really great open source projects that are out there.
But what are some of the questions people should be asking when they're evaluating inference services?
It's what is the, you need to have like a very clear understanding of what are your like quality of service objectives that you want to hit, and what is like quality of service both in terms of like the accuracy of the responses and the latency, like the responsiveness of the server, because that kind of with all of these, right, like with I guess with latency, throughput, and accuracy, there's kind of like a Pareto frontier that you have to build for yourself, right? Like you can give up one to gain the other, and you have to have like a very clear idea in your head of like what you're optimizing for, right? So in one extreme, you could be like, I just want the highest throughput thing, right? Like the absolute cheapest thing to run, especially if you're running offline. I'm just going to crunch through a bunch of data and do it. Maybe that's the part of the problem space that you're operating on. If you're working on something that really needs low latency, then that's the part of the space you have to operate on. Or in some cases, it could be that you need the absolute highest accuracy, right? Like, and you don't want to mess with any of these. So you have to kind of decide where in this problem space you want first, and then that kind of informs a lot of the decisions that come.
Thank you. So one last question before we move on to Phil. So when we got the audience questions, there are like two category of questions. I got a lot of questions. One is just like multi-GPU optimization, and the other is single GPU optimization. First of all, trying to like fit in as many models on the same machine as possible. So from the perspective, which directions are you more interested in, and which will be more common in the future?
Yeah, I mean, I don't think there's any avoiding multi-GPU models. Like people are just making models bigger and bigger and bigger, and however much, whatever fancy techniques you come up with to try and fit it in one GPU, they're going to build it. They're just going to use it to build a bigger model. So there's no non-multi-GPU, like, or we can't ignore multi-GPU. That there's just no way to do that. But there are many ways in which you can make many cases in which you can a single GPU is just fine, right? Like you can quantize things more aggressively. In future generations, GPUs are getting bigger and bigger, like the memory that's available on them is bigger. So the same model that needed to previously could fit on one. Both of those are really important. Certainly for among developers, single GPU is like by far the most important because it's just the easiest one to run.
Cool. Thank you so much, Sharan. So there are questions on Discord if you have time to answer, but we appreciate your presentations. So for the next, we have Phil Tillet from OpenAI, who is the creator of Triton, OpenAI Triton, not NVIDIA Triton. And he's really talking about the philosophy and the design of Triton today. So I just saw that when I was looking at Phil LinkedIn before the talk, I realized that like before joining OpenAI, he was interning at literally every chip maker company out there. So yeah, okay, welcome, Phil.
Yeah, thank you for having me. Can everybody see my, and it's not full screen. Let me put it full screen. if I figure it out. Can everybody see the screen now?
Yeah.
Yes.
Okay, great. It works. Yeah, so first of all, thank you for having me. It's my pleasure to give this little talk. Yeah, so as Chip said, I will talk a little bit about the philosophy, the design, and sort of like how Triton works. And I think the core concept behind Triton is this thing of like block-based programming, which is like this new programming model and this new way to think about algorithms and how they map to parallel hardware. So the first thing you might wonder is like, why would you want like a new programming language in the first place, right? There's already so many out there, so why do we need something new? So I love CUDA. I've been doing CUDA for a lot of my life. And the way I would describe it is you get a lot of flexibility, and it all comes at the cost of the simplicity of your program. So one good thing about CUDA is the developers can sort of do like whatever they want. So they have like very, very precise control over what each thread on the GPU is doing, what memory it loads, how it interacts with other threads on the GPUs. And you can sort of use that to squeeze out the very last bit of performance out of your GPUs if you want. Another good thing about CUDA is you can sort of like use whatever data structure you want. So you want to walk a tree, you can do that. You want to traverse a linked list for a KV cache or something, you can also do that. So it also gives you like a whole lot of flexibility in terms of what you can express functionally, what you want your algorithm to do. But the drawback of this is sort of the same thing, is, oh shit, developers can also do whatever they want. So performance optimization is like super cumbersome and very time consuming. And I've written a lot of CUDA myself. I've worked with a lot of people who've done CUDA too. And I think doing anything advanced enough in CUDA just takes like a whole lot of effort. It's like moving a mountain. And I think that can like really hamper productivity quite a bit. And sort of a consequence of that is code bases tend to become extremely complex and also very hard to maintain. So one thing that's sort of typical when you deal with CUDA code base is for the first few months, it's going to be sort of okay to maintain. And the more GPUs you need to support, the more algorithms you need to support without like sort of like breaking backward compatibility or like still supporting all things that might still have use cases. All of this just becomes harder and harder to maintain. So that's not great, because then it means that doing any sort of change takes a whole lot of time. And this sort of like prevents companies from like moving really quickly, especially in research orgs. And finally, I think a third big drawback of CUDA is it's sort of completely opaque to researchers. So if you want to even read, if you want to even like be literate and be able to read CUDA code, you sort of need basic training at the very least. And if you want to look at code that uses tensor cores on MP or like warp groups on like Hopper and like whatever come next on the next hardware architecture, then you need to be like very proficient, if not an expert. And obviously, it's not something we can request researchers to be. So you end up with this disconnect between what sort of like CUDA kernels become this black box that researchers don't even dare to touch. And this also tends to slow down the pace of research in orgs like OpenAI. So I think all these problems, people have been aware of them for a very long time. And something that a tool that people have come up with to address a lot of these problems is graph compilers, or like even things like PyTorch that have graph representations of your programs. And this is like much better for research, because like there's a very fast iteration speed that researchers can do. So they can express ideas like in an afternoon of things that would probably take weeks or months to write in CUDA. So that's very good. But the drawback of that is that, first of all, they cannot represent all the types of ideas that they want. So again, I'll go back to the paged attention example that was mentioned before. Is like if you want to traverse a linked list in PyTorch, or like walk a tree in PyTorch, it's going to get like very, very slow at best, because you're going to have to keep reading tiny tensors, and it's going to be probably slow to the point where it's not really usable in practice. Another thing that you cannot really express with graph level compiler is stuff like control flow that happen in the operators. So for example, you might have like a matrix multiplication kernel or something, but let's say you want to like skip the computation of certain blocks of your output based on some condition that's only known as runtime because it's data dependent or something. It also becomes really hard to represent that with graph level operators. And sort of like another issue that's not very fundamental to graph compilers, but that has arisen a lot in practice is just code generation of CUDA code from graph compilers. It's a very difficult problem. And yeah, and this is why you have things like flash tension that have like custom CUDA kernels, although I think in principle you can represent them using graph level compilers. So yeah, so Triton is sort of this thing of like meet me in the middle of like I want to be higher level than CUDA, but I want to be lower level than a graph compiler. So it aims to be simpler than CUDA, but also like more expressive than what you'd be able to do with your typical tensor level operations.
Well, Phil, I think my choose a slice is not advancing. Is it on? Not sure it's on purpose.
Oh, it's not advancing. Oh, okay. Is it fine like this if I just slide like this? Is my screen frozen?
No. It's moving when you were scrolling it like that. That was okay.
Yeah, that's not ideal. It's a PDF. Give me a second just to try to fix this. I don't have that many slides anyway. I'm sort of just gonna share my entire screen and hope it works this way.
Yeah, maybe you can see some OpenAI secrets.
I hope not. Can you see now?
Yes, it's much better. Thank you.
Okay. Yes. Now I have even like the fancy animations and so on. Okay. So where was I? Yes. I guess you didn't see all the slides I had before. But I think, yeah, basically graph compilers have like a lot of simplicity at the cost of flexibility. So everything I said before. And with Triton, you sort of try to be in the middle of these two worlds where you're going to be simpler than CUDA, but you're also going to be like more expressive than graph compilers. So the idea is that you'll do in days what would take you weeks or months to do in CUDA. Maybe it might take you like hours to do with like PyTorch or something, but the intuition is maybe we're able to tolerate days to write certain kind of workloads if we can get the performance and the expressivity that we want. And the good thing about this approach is you can sort of write algorithms that are out of the scope of typical graph compilers. So as I mentioned, like you might want to do like a radix sorting of an array, or you might want to walk a tree, or you might want to traverse a linked list. You can go crazy with like sort of the data structures that you can use. And a very good positive aspect of that is like because you've sort of raised the abstraction level, the code can still be understood pretty well by researchers. So they can read it, they can modify it if they want. They can even write it from scratch in some cases. So that's another big upside. And finally, obviously, you become like more performance portable across different vendors because now you've raised the abstraction level of your program, and now like it uses language constructs that are sort of portable across different hardware vendors. So yeah, and I think another way to think about the performance of Triton is because it's at this middle level. It's like if you spend enough time on your Triton program, usually you can get performance that's at least as good as what a graph compiler would output. Obviously, the counterpoint of that is now you're less expressive than CUDA, and you're also like more complicated than a graph compiler. So there's trade-offs in everything, and the most obvious trade-off is now like CUDA is the upper bound for the performance of Triton, and if you spend enough time on CUDA, might be a month, maybe 6 months, maybe a year, yeah, you're going to be able to get performance that's at least as good as what Triton can generate. And another drawback of that is you also iterate slower than if you use a graph compiler when applicable. So Triton is not always like the right tool to use for your workload, but like if you want this mid-level layer that's like a little bit simpler than CUDA and like a little bit more expressive than graph compiler, then it can be pretty helpful. Okay, so I've spent some time motivating the existence of Triton, and now I ought to talk a little bit more about what it actually is. So maybe the first thing to keep in mind is the machine model under which Triton operates. So essentially, this is what Triton can generate code for, like any architecture that has these basic design principles. So it's a fairly standard like von Neumann architecture that's been around for like, I'd say like at least 20 years with multi-core CPUs on the consumer side. And essentially you have like an off-chip component that contains like random access memory that's like reasonably fast, but like not extremely fast. And that has low latency just because it's like physically very far from the compute. So the light and the signal has to travel at a certain speed to reach your arithmetic units. And then once you're on the chip, you have this basic architecture of like having some memory controllers that interface with the memory and dispatch the data to different cores. And then different cores can sort of do their thing in parallel. And each core has like a cache so that if it needs the same data twice, it doesn't need to go through the memory twice. And all the cores have an L2 cache that's sort of shared together. So that's the basic like machine model that Triton uses. And in Triton, what you're really doing is you're programming each core. So I cannot see my cursor, so I cannot highlight this, but you have all these purple segments and you're really programming those individually. And in CUDA, it's a little bit different because you're actually more programming like the vector units of each core. So you have to manage the L1 manually and so on. And once you have the programming model, you also need to like sort of define a programming model. And the programming model of Triton is basically that users define like tensors in the SRAM of the GPU. So if you look at PyTorch, the tensors sort of live in the DRAM of the GPU, and then you have operators on the tensor that live there. In Triton, they live in these light blue blocks. And then other than that, it's very similar to PyTorch. So you can still modify them using like tensor level operators like reductions, element-wise operations, matrix publications, sorting, and so on. Maybe some like important characteristics of Triton is it's embedded in Python. So I don't know if you've heard of Numba, but it's sort of like a similar-ish projects where your kernels are sort of defined as Python function, and then you have a little piece of code that parses the syntax tree of your function and generates code for it. And this is sort of how Triton works. So whenever you call a Triton function, the Triton compiler will parse the AST and like specialize it for the data types that you pass to it, generate code, and then run it. Another specificity of the Triton programming model, if you want to compare it to PyTorch, is you have pointers. So if you want to walk a tree or iterate through a linked list or something, you kind of need pointers instead of just like pure like index-based semantics like in Torch. And so typically in Triton, what you do is you construct like a tensor of pointers, and then you do like dereferencing the pointers element-wise. And finally, maybe the last big difference with PyTorch under this programming model is there's some pretty strict constraints on what shapes the tensors can have in Triton. And the specific constraint today is that all the shape of the tensors must be powers of 2. And we'll sort of see how this maps in practice and how you can still handle tensors, torch tensors of arbitrary shapes with tiles that are like very constrained. So now I have a couple of examples that I want to go through. So the first example is vector addition. So very simple pointwise kernel. We're going to assume right now that we're running on a single core and that there's no bounds checking. So you import your Triton language and your Triton functions and so on. And then, as I said, it's a decorator. So you annotate the function with this Triton.jit decorator that essentially tells the Triton runtime, or whenever you call this function, don't actually run it, but like analyze its syntax tree and generate code for it, and then run the code that you've generated. And then once you're in that function, you can pretty much like do things very similarly to how you would do them with Torch, but using the TL namespace and respecting these constraints I mentioned earlier. So in that case, you create, essentially your goal is to create an array of pointers for each operand, and then you're going to dereference these pointers element-wise. You're going to do whatever you want on them, and then you're going to write them back. So here you can create like the 3 arrays of pointers that contains like 10, 24 pointers to each of the operands. Then you can call tl.load to sort of like dereference these pointers and get like Triton tensors of values out of them. And then at this point, X and Y actually live in the SRAM of the GPU. So maybe like you can think of it as the L1 cache or the registers or something. It's up to the compiler where they actually reside physically. But the point is, once they're in the SRAM, you can read them very quickly. So you don't need to worry about like reading them twice from SRAM or something. So then you can do your business. So in the case, you can just add the 2 tensors together, and then you can just write back to the tensors of pointers determined by Z. And then there you go. You have a simple Triton kernel for an element-wise operation. Then you can create your torch tensors, and then you can sort of like run this kernel. Here, there's a grid size of 1, because as I said, we're only running this program on a single core. So one way you can sort of make this a little bit fancier is you can say, okay, now I'm going to run this Triton program on multiple cores of my GPUs in parallel, and I'm going to handle like arbitrary values of n, arbitrary input size for the vectors. And in that case, the program just has to change a little bit. So now whenever you launch your program by calling the function, you have to specify a grid that essentially corresponds to the number of program instances that you want to run. So in that case, you can run, I don't know how that's going to be, like 170 instances or something of your program. And then it's just every instance is going to get a program ID. And within the kernel, you can create this program ID. So you can sort of use that to make sure that each program instance has pointers to a different slice of the inputs. And you just need to make sure that the last program instance that processes the last slice actually doesn't read data out of bounds. So the tl.load can have a mask that you can give just to make sure that you don't load data and store it out of bounds. Yeah, so now it's pretty similar to before, except that now you can sort of handle arbitrary input vectors of arbitrary size. One last thing that you can do is you can say, well, maybe like this block size that I set to be 1024 before, I can actually make it generic. So in that case, you can add an extra argument that's a constant expression, and you can use this to parameterize your kernel. And then when you create the grid, you want to make sure that the grid is properly set as a function of this block size. Yeah, so if you do all that and you run this kernel on different input sizes, you'll see that you get exactly what you'd expect, which is that like when your vectors are really tiny, you get really low bandwidth because you're essentially latency bound and you cannot use all the cores of your GPUs. You basically don't have enough work. Then the more work you have, you start to ramp up linearly, and eventually when the size is big enough, you plateau at the physical nominal limit of your HBM bandwidth or your DRAM bandwidth. And you can also do the same on AMD. That the same code will just work on AMD, and you sort of get the same performance profile. Another example I want to like quickly gloss over is the softmax. So for the softmax, we're going to reuse the same programming model as before, but now what we're going to do is each instance of the program, instead of computing a slice of the input vector, is going to compute a row of the output vector. So here, like PID means program ID. And we're going to do something fairly simple where every program ID processes a different row and computes a softmax on the different row of the input. And the nice thing with this is you can load the entire row in SRAM, and then you can sort of do like whatever amount of mathematics you want on this block of data. It's sort of like by design going to be fused. So very similar to before. You create your kernel as before. So there's like, you want like the pointer to the output Z, the pointer to the input X. You want the stride, that's the distance in memory between two rows of your output and your input. You want N, which is like the number of columns of your matrix. Yeah, and very similar as before, except that this time the pointer arithmetic will be like a little bit different because you first need to offset with the row, and then you have a vector of pointers to each value in the columns. So then you load it as before, and then you do your softmax mathematics. You just like subtract the max, exponentiate, and normalize. And then you can sort of write back to DRAM. And the good thing with this is you notice that you've actually loaded your data only once. So it's more efficient than if you were like doing all this back and forth to HBM. Like if you're using PyTorch eager mode, for example. Obviously, it's something that PyTorch compile can do automatically, but this is sort of like the bottom-up approach of what PyTorch actually ends up generating. Yeah, and if you do that, you can see that you actually get like better performance than Torch eager because you're only loading your data once. And I didn't benchmark Torch compile, but I would expect it to be similar to Triton here. There's no reason why it wouldn't be. And again, you can do the same thing on like AMD GPU, and it's going to work, and you're going to have like very good bandwidth as well. Yeah, so I have like 6 minutes left. So I have a section that's sort of like how it works internally. I try to go over it quickly. Yeah, so I think one thing you might wonder is why are blocked program like sort of so powerful, and why is the compiler able to do so much with them to the point where something like Torch Inductor can generate Triton and get like good performance in both cases. And I think there's three fundamental reasons why that's the case. I think the first reason is it sort of like enables something that we call like people optimizations, which is like patterns that the compiler can recognize. The other fundamental point is like the compiler can manage the SRAM, and it can sort of do that very well. And the third point is it can automatically vectorize your code. So when I say people optimization, what I mean is like, yeah, as I said, your compiler can recognize patterns at the block level that do not necessarily happen at the scalar level. So one example is you might have like two transposes that you do back to back, and now your compiler can realize that this cancel out. But if you are in CUDA, your transposes wouldn't really look like transposes anymore, so the compiler wouldn't be able to tell. And there are a bunch of other patterns that you can recognize as well. Then another thing I mentioned is when you write CUDA, you have to sort of like manage the shared memory manually, and that can be very complicated to do. So in Triton, the compiler can sort of like analyze what we call the live range of each tensor, which is essentially at which point in the program you need it and when do you not need it anymore. And then it can move the instruction to the program so that all these live ranges sort of work well with each other, and you don't need too much memory at the same time. And finally, the last point it sort of helps with is automatic vectorization. So for example, if you had like a multi-dimensional block of pointers, then the compiler can recognize all the values along the columns are actually adjacent to each other. So maybe I can just like treat them as like a smaller number of vectors and do like everything at the vector level. And this is sort of how you get like good memory efficiency with Triton. Because when we talk about memory coalescing on GPUs, what we really mean is GPU memory interfaces have very large bus width. So you want to make sure that whenever the GPU issues a load, it issues a big enough load to keep the memory interface busy. And by doing this sort of analysis, Triton can make sure to generate like very large loads that can sort of keep the memory interface busy for a while and use the bandwidth efficiently. Yeah, and finally, like now that we've seen like how it's powerful, I think another question that's worth asking is, okay, why is it so powerful? So what does it actually enable in practice? And one thing I found like very interesting to observe at OpenAI is there's a lot of value that we can have in just like letting researchers do their own kernel development. So if you do everything in CUDA, and if you have a centralized team that takes care of all the requests from all the researchers, then what you'll see is the amount of work that you have to do in that team sort of grows linearly with the number of IDs that researchers have. And that's not very scalable, that's not very good. And when the company is very small, that works really well because it's a linear function that starts at 0. But as your company grows, this can become very hard to maintain. And of course, as the number of GPUs your company use grow, this is also very hard to this is a pretty insane mode of operation. And Triton, in contrast, what it does is it say the maintenance of the maintenance burden as a function of the number of researchers in the company and the number of different GPUs that you use is sort of going to be constant. So it's a very large constant because it means maintaining a compiler, but it's a constant. So when your company has enough IDs or enough people, then it actually starts to be worth it. And of course, you can always hire more to try to help with this issue. But when you hire more on like a very low level code base with a centralized kernel development team, what you just do is you just reduce the slope of the maintenance burden, or you reduce the y-intercept if you maintain a compiler. So even if you have infinite headcount, it's still like a sane approach to pursue. Another thing I found like super valuable with Triton is it really helps keeping the technical debt in check when you maintain a kernels library. So one thing I do at OpenAI is I not only maintain Triton, but also maintain the kernel library that we use for training. And one thing I've seen sort of like over and over again with like low-level programming languages is like the code base becomes very hard to maintain very quickly. And I've sort of used this this meme that I love to illustrate that is at some point you can every single thing that you want to do and every way you want to touch the code base becomes extremely painful and makes your employees unhappy. And with Triton, you can sort of keep a more sane library code base. At least for me personally, in what I've managed. And yeah, and finally, I think one good advantage of Triton is it's going to allow you to get very good performance rather quickly. So I've illustrated with this little graph here is showing the performance that you can expect out of your application as a function of the time you invest optimizing it. And you can see that yeah, you can take the approach of writing everything in SAS, which is the assembly for NVIDIA GPUs. It's going to take you forever, but you're going to get very good performance at the end. Alternatively, you can use CUDA, and in that case, it's going to take you still a long time, but not as long, and the performance is going to be like a little bit lower. Or you can use Triton, and in that case, it's going to take you even less time to get reasonable performance. But then if you want to actually get like the absolute last 2% performance that you can get, then that is going to be very painful to do that. Yeah, so I think that's all that I have.
Thank you, Phil. Perfect timing. I've been really impressed by how all the speakers have been keeping their talk exactly 30 minutes until now. So Phil, so I have a lot of questions. So I'm not sure if you can share, but like, what are some of the challenges of like building kernels to train models at OpenAI scales that surprised you?
Yeah, so I can talk a bit about that. I think it touches on like the last points I've mentioned, which is when you're at OpenAI scale and when you're a research org, I think the one thing that you really care about the most is reliability of your code base, and sort of how agile it is. Because the two things you want to avoid is, one, you have a bug that's going to stall your big training job for like a few days, and everybody's going to have to fight fires to fix it. So the more reliable your code base can be, the better, and the more people can look at the code base to find bugs, also the better. So I think that's been one of the very big advantages of Triton there, and why we've fully embraced it for training. Yeah, so what else? Yeah, and I think another big aspect is just like another thing that can happen when you're at OpenAI scale and you have a lot of researchers is one day like there's a research breakthrough and it's like, oh, this very complicated idea actually works or something. And we need a kernel for it as soon as possible. If you can get it done like this week, it's actually good. And I've had like several cases for this before. And it was like super helpful to actually be able to write these kernels in like a week, even if they were like complicated. Maybe one example I can give is like flash tension. So when flash tension came out, yeah, a bunch of people were like, oh, this seems like it can be helpful. Can you write it, Phil? And yeah, obviously, like we had like a slightly custom kernel, so I couldn't just use CUDA, and with Triton, I was able to get it done like fairly quickly.
Thank you. Mark, want to go next?
Yeah, Phil, I actually want to ask you a question on the other side of the spectrum, which is like more like in the sort of single consumer GPU setup. Like, have you noticed like any tricks that like are particularly important in Triton to like achieving strong performance on like 3090s, 4090s, that like differ substantially from, I guess, the typical hardware you might be running in CI?
Yeah, I think it's kind of interesting because the consumer GPUs have a very different performance profile from the server GPUs, and maybe the way in which they differ the most is in the restrictions that they have on tensor cores. So on consumer GPUs, if you use tensor cores, you get much better performance if you accumulate in 16 bits of precision. And on server GPUs, you don't have this restriction. So I think what this means in practice is on consumer GPUs, you want to go out of your way to use the 16-bit tensor cores, even if this means like doing some periodic renormalization of your accumulator or something. And this is something we haven't really like prioritized for Triton, because at OpenAI we don't really use consumer GPUs. So for a long time we didn't even support these FP16 accumulators, but nowadays we do. And you see some companies that that are very focused on consumer GPUs. Maybe one example is like TinyGrad as a project that focuses on consumer GPUs, where if they really want the best out of their GPUs, they have to do these tricks.
Oh, thank you.
There's a very interesting question that I saw is that like actually a few people ask the same questions. Is like usually model performance or like behavior can change after the automation process. Like how do you ensure or like detect or like maintain the consistency of models?
Yeah, I think that's a great question, because it ties back to the point I made about avoiding bugs being one of the most important things out of OpenAI. Is you want to make sure that when you make your code faster, you don't actually make the training process diverge. And the way we usually do that is you can look at your kernel and you can look at the operations it does and whether or not it should produce the same output bitwise. And one strategy that's sort of salient there is whenever you optimize a kernel, and it shouldn't change the output at all, literally, then you want to check that the output is bitwise identical to what it was before you optimized. I think that's probably one of the most potent tools in the toolbox to check that you didn't break anything when you optimize. Obviously, you can always check numerics, but checking with numerics, checking numerics for quantized data types like FP8 is really tough. So what I usually do when I have to test correctness for FP8 is I set like some of the mantis bits to be 0. So essentially I only test with power of 2 inputs. And then you can make sure that if your reduction depth is small enough for a matmul, then you don't have any rounding error. And the result should be bitwise identical to the FP32 reference implementation. So I think usually, yeah, these are the tricks I personally use, is making sure that things are bitwise identical when they should be.
Thank you. So the questions that got a few upvotes is just like, so it's from the talk, a lot of tools that we touch on. So for a company, so say like, how do you, so like for companies that want to like just fine tune, or the company just want to self model, and the company just like train the model from scratch, like what would be the different tools you should start with?
Yeah, I don't know if it's a question for me, because Triton is not really like a framework, so it can help you write kernels for training, can help you write kernels for sampling, but at the end of the day, it's the language. And if you want to fine tune a model, you need like a framework on top of it that can handle the backprop for you, and the orchestration of the GPU work for you. And this is out of the scope of Triton.
Have you seen any like surprising kernels that people build on right on top of Triton?
I've seen a bunch internally, but I cannot share. Okay, there was one surprising kernel that was upstreamed. It's not really a kernel, but it's a primitive that was upstreamed. And that surprised me because I didn't even know it was possible, but it's sorting. So for the longest time, I thought you couldn't do sorting in Triton without a custom instruction for it. But somehow, like somewhat found a way to implement it in Triton using like hypercubes or whatever. And when I saw that, that surprised me because it was the first instance of people becoming better at writing Triton than me, which I think is a milestone when you make a custom language.
Okay, so one last question is, I want you to understand more about the design process of Triton. Like, what did you land on the block base, and how did you choose the block size?
Yeah, so I think historically it's kind of a long story, but the way it went is I did my PhD, and I wrote a code generator for matrix multiplication. So this code generator generated PTX, which is a virtual assembly language for NVIDIA GPUs. And over time, like I did abstractions for this code generator, and it started looking more and more like a compiler. And one day I was like, okay, let's just make a compiler on top of these abstractions. And this is how Triton was born. Now, when you want to find the right block size in this model, it's a little bit tricky because there's a bunch of things that are outside of your control. It's how the Triton compiler behaves, also like how the PTX compiler from NVIDIA behaves. There's a lot of factors that you cannot really control. So the way I typically approach this is I just auto-tune different block sizes and pick the best one. Another like rule of thumb that I think works well is you can pick the biggest block size that fits on your GPU. So as soon as you start spilling registers, you just reduce the block size. And this is another like heuristics I've been using that works well.
Thank you, Phil. So there's one question that I hope that Mark and Phil can help answer on Discord. It's just like the consistency of like PyTorch kernel and Triton kernel. But now let's move on to William. William, are you here?
Sorry about that. Yes, I am here. Had a trouble finding my mute button.
Welcome, William. He's a co-founder of Voltron Data. He has been working on GPU optimizations for query engines many years, like for many years. I believe you started with like BlazingSQL, and now you're working with Voltron Data. And if you people work in data science, you're pretty familiar with a lot of tools like Pandas, scikit-learn, Spark, and a lot of those tools are not like optimized for GPUs. And in this talk, William's gonna walk us through like through different GPUs optimized in alternative for this tool. So yeah, welcome, William.
Thank you, Chip. Yeah, so in this talk, I mean, the way that I see this talk is more about like if you're thinking about going from a CPU-based data processing over to GPUs, kind of some things to
sorry, I'm not
think
sure
about.
it's intentional, but you are sharing your Chrome.
I'm sharing my Chrome. Oh, okay. Sorry, wrong one. Thank you for pointing that out.
Good plug for IBSL, so.
There we go. Is that correct? I'm sharing.
Yeah.
Okay. All right. Sorry about that. Yes. So this talk is more about if you're thinking about moving from GPU processing to GPUs, so some of the reasons to consider why to do that, and things to consider if you want to go beyond that and scale up to distributed GPUs. And to kind of start that kind of thought process is like, okay, GPUs versus CPUs versus GPUs. Obviously, y'all know CPUs are good at everything. They're on every server. You absolutely need them. They're generic. They're easy to use. They're a lot less expensive. They're actually quite fast. They offer very low latency. But where GPUs come into play, and they can be a lot better, is at doing all the same thing over and over in parallel. And they kind of prefer to deal with data that's a little bit more structured in terms of like vectors and arrays. Now they do have a little bit more latency in how you interact with it, but they offer extremely high throughput. The analogy that I like to think about is like, CPUs are like your UPS truck. They can stop at every little house, packages of all sorts of different sizes. GPUs are more like a shipping truck, more about the same amount of data going from one point to another. You're getting like a lot of throughput from one point to the other. And the more data that you're putting into it, the more you're processing at a time, the more you're going to be able to do. Another analogy that I have that I like to think about is also from the database space. There are what you think about like transactional databases versus analytical databases. Transactional, sometimes you refer to them as OLTP, online transactional processing, versus OLAP, online analytical processing databases. Now, transactional ones tend to be more row-oriented because you want to optimize for inserting data, deleting data, modifying data, usually one row at a time or a couple specific rows at a time, which means that you're holding your data in a row-wise fashion. Now, think these sort of databases are more like MySQL and Postgres, or if we think about it from a file format perspective, CSV files are row-oriented. The way that the data is serialized on the file is in a row-by-row fashion. These are typically not very GPU-friendly type of problems. While on an analytical database, they tend to be column-oriented because usually when you're doing an analysis on a set of data, you're often only looking at specific columns at a time or doing things with columns of data. Classic database column or databases include things like Snowflake and Redshift, and file formats that are also column-wise would be something like Apache Parquet or Apache Orc. And when you have your data organized in that way in columns, then it becomes more GPU friendly. Even on the CPU side, they're more SIMD friendly as well for vectorization. And that's kind of like the sort of data type of problems you want to do with GPUs. Now, speaking of column-oriented, I want to talk a little bit about Apache Arrow. Hopefully, some of y'all know about Apache Arrow. It's basically the most popular columnar and memory format representation. It is used by most data analytics frameworks and tools nowadays, or at least to be able to input or output data as Apache Arrow, because it is very easy to operate both with modern CPUs and GPUs. It offers like zero copy transferring, which means that if you're interacting between a lot of different data analytics tools, you can pass data from one tool to another without having to serialize or deserialize. Sometimes you can even avoid the copies entirely by using sort of zero copy data transfers. So in general, piece of advice, if you're ever like trying to look into different frameworks or tools to use, consider ones that do play nicely with Apache Arrow, because it'll make the interactions with any other tools you might have in your system be a lot more seamless. And it's not going to go anywhere. It has about over 100 million downloads a month. So GPUs can accelerate a very wide variety of data processing workloads. And I kind of want to show you a couple of different slides. By the way, these are slides from NVIDIA Rapids, which, if you don't know NVIDIA Rapids, it's a very high performance NVIDIA GPU library, but they have a lot of different libraries mimicking a lot of different popular CPU-based libraries. This slide deck is actually about like 4 years old, from near the beginning of when Rapids became public. But I want to illustrate here is just how powerful and how fast GPUs can really be, and the wide variety of things that they can enable us to do from a data analytics perspective. So in this particular case, we're talking about CUDA, which is one of the Rapids libraries. It's very, very similar to Pandas. Like, the APIs are virtually identical. And you can see that in this benchmark, you'll see the purple columns and blue columns. You can see like it's basically different amounts of data. And the y-axis is actually a multiplier of how much faster CUDA is over Pandas. And you can see, like, we're talking more about like 2 orders of magnitude performance difference. Now, granted, GPUs are more expensive, and we'll get to more like price parity comparisons later, but it's just impressive to see like the sort of differences that we have here. Now, the different things we're getting benchmarked here are group bys, sorts, and merges, which merge from a Pandas perspective is similar to a join and SQL land. But these are very much part of the bread and butter of a lot of data analytics that you do for especially like ETL. Now, there's also another library like CuPy, similar to NumPy, which is more for numeric array operations. Again, if you're dealing with ML or AI, you kind of have to do your ETL. You have to prepare your data. And you can see here things like FFTs and array slicing, matrix multiplications, and different types of operations can be accelerated more than others, but you can still see, a pattern of like 1 to 2 orders of magnitude faster. Again, note that you see a lot more performance improvement the more data you're analyzing. Also note that this is on a logarithmic scale. Similarly, there is cuML, which is similar to very popular framework scikit-learn on the Python side for machine learning. And we see, like, again, similar, in some algorithms, perhaps only, a couple multipliers. But for some, the performance difference is truly significant as well. And again, you see this pattern of the more data that you're processing much faster. Here you can see like linear operations like k-nearest neighbors, or on the other side, you can see principal component analysis, linear regressions. All these things can definitely be made significantly faster with GPUs. Finally, here is a slide about cuGraph, which is more of like a graph analytics library, very similar to NetworkX, which is another popular library. Here, the multipliers are just astounding. And I know that the numbers are really small to see on the chart. So some of the highest numbers here on the chart are like 25,000 times faster. Some of the lowest ones are maybe like 500 times faster, but it gives you an idea of how much performance gains you can get out of GPUs. And apologize, my graph analytics is not really my specialty. I'm showcasing this as more as examples of different types of data analytics things you can do, and you can usually get a really big performance difference. One other type of analytics that's very popular as well, unfortunately I couldn't get a slide for that, is reading files, like reading and deserializing Parquet files or CSV files. You can also get really high performance in just accelerating all of those as well. And now, obviously, this isn't just rapids. There are all sorts of GPU accelerated libraries out there, depending on what it is that you need. So if you're coming from a more CPU typical processing and you want to explore GPU processing, whatever library that you're doing, there might be either that library might already support GPUs, or there might be similar libraries. And I encourage you to kind of look and investigate for yourself. The amount of GPU accelerated libraries that are appearing all over the place just keeps growing every year. A couple mentions here, PyTorch, we've already been hearing a lot about. ArrayFire is another one for general purpose parallel computing. TensorFlow for machine learning. Numba provides kind of like a just-in-time compiler for accelerating Python code. Bend is a new popular, massively parallel high-level programming language. XGBoost is very popular on the CPU side, also can be accelerated using GPUs for doing machine learning with distributed gradient boosting. And Voltron Data's Thesis SQL engine does, as the name implies, SQL data analytics, also accelerated by GPUs. And so all these massive multipliers that we're seeing, how are we getting this? How are GPUs so fast? As many of y'all know, GPUs have a lot of cores, but it's a lot more cores. I mean, we're talking about 2 orders of magnitude more cores than high-end CPUs have. So that's like one of the reasons why they can do so much more work more in parallel, and why that's what they're designed for. It's for parallel work. What's perhaps a little bit less known is just also the memory bandwidth of the memory in the GPU is so much faster than the fastest, more CPU-based memory. Now, I'm not talking about, L2 and L3 caches. I'm talking more about like the main body of the memory that you're interacting with. You'll find that's about 20, 30 times faster memory bandwidth on the GPU, which means the amount of cores plus the faster the memory gives you an idea of like why it is that GPUs can process memory so much faster. Oh, I'm sorry, process data so much faster. So if they're fast, should we always be using them? That's not necessarily the case. There's a couple situations where that's not necessarily a good idea. So like I said, CPUs are better in terms of latency, especially if you're dealing with having to process lots of very small things and return results really, really fast. CPUs are probably going to be a better option. Also, if you have a data processing problem that is extremely I/O bound, and I/O can here mean more like you're reading from a storage device somewhere, or maybe just pulling something from the network. If your problem is extremely I/O bound, having the power of a GPU is not necessarily going to help you because your bottleneck is still going to be in the same place. The cost of GPUs is also something that you have to consider, see if it's kind of worth it. And ultimately, if you don't have that much data, it just might not be worth it. But if you have a fair amount of data, and if you have a data processing problem that is compute bound, then GPUs are probably what you really need to, you really want to use GPUs. What's interesting though is that once you do switch to GPUs, very often your problem is no longer compute bound. And you may end up realizing that you now have an I/O bound problem. And then you have to figure out like, well, how do I make my I/O faster? And there's different ways of making your I/O faster with GPUs, and we'll touch a little bit on that. But now it becomes a different types of optimization. Here I'm thinking more like system level. I'm not necessarily talking so much about lower level algorithms as some of the previous talks. But another thing to consider is also if compute density is important for you. And I'll touch on that a little bit later, what exactly I mean by that. But also just the speed. If the throughput speed enables you to do more, or if you're using GPUs anyways. A lot of folks here have probably realized that ML and AI in particular are so fast when you're able to do it on a GPU. But sometimes some people still are doing some of their ETL side of work with CPUs. Well, I encourage you to see if you can do some of that ETL, data transformation, feature extraction on GPUs as well. That way you're leveraging the hardware for both sides of your problem. And let's kind of see a little bit how this plays out, because like as I said, the doing more processing faster, like speed in and of itself isn't that useful. It's more about what can you do. Like, can you do more scale? Can you, like, say for example, you are doing some training and you can only you have to subsample your data because otherwise it's going to take too long. If you use GPUs, you can process much faster, and maybe you can use all your data rather than doing subsampling, or you might be able to iterate more. This slide is kind of telling a story about a data scientist that's doing some ETL to go train some models. And in this CPU-powered workflow, the green segments are talking about the ETL side of things. Then the analyst looks at the analysis and the red parts of the diagram. You can see like sometimes do some ETL, do some analysis. Oh, you realize you need to add something else. You do more ETL, you do some analysis. You do that over and over again, with the idea that if you did that with the GPU, you can do a lot more of these iterations, because that time of that analysis processing just gets so much smaller. It can really accelerate a lot of things. There are certain types of data analysis that become more close to real time when you're able to harness the power of doing more GPU-based processing. Now, a lot of this, obviously a lot of these problems, and when a lot of the previous slides, it is very, very fast when everything kind of fits on your GPU. If it doesn't fit on the GPU, then you have to be moving data in and out, process things in batches. You have to be creative about how your entire workflow, you can do it in and out. And things actually also then get more complicated if you have to go, if your amount of data is so big, you actually then have to go to multiple GPUs and sometimes distributed GPUs. And so I want to talk about that a little bit and some of the challenges that and considerations to have there. And why GPUs also make sense in that case. So in this slide, I want to show you a little bit about this benchmark called TPCH. TPC is an organization that puts together a lot of different benchmarks, primarily for databases and other like very large scale data analytics tools. And the TPCH benchmark in particular consists of 22 different SQL queries. And in this case, here we're doing a 10 terabyte benchmark and just changing the different number of nodes. And as you can see, obviously, the more nodes you add, the more workers, the faster it goes. Obviously, your cost also increases. But you see, it ends up getting up to an asymptote, meaning it gets to a point that you can't add more workers to make it go faster. And part of that has to do with the fact that with distributed systems, all these workers have to be talking to each other. So the more workers there are, the more overhead there is in the communication. Now, what happens when we do this with GPUs? In this case, same benchmark, but now we're looking at a couple of different data sizes, the same 10 terabytes, but also looking at 30 terabytes and even 100 terabytes while using Theseus from Voltron Data, compared again to Spark. And you can see, and actually, I don't know if y'all can see my cursor or not, but in the middle, you see basically a black 8 right on top of a pink 40. And those are basically at price parity. 8 GPUs ends up costing about the same as 40 Spark workers. So GPUs are more expensive, and that's one of the things you have to consider. But those same 8 GPUs are doing about the same amount of work. Well, actually, no, it's not the same amount of work. It's 10 times more. That's the 100 terabytes using Theseus as about as close to what Spark is doing for 10 terabytes. It kind of illustrates like how much faster you can process things with GPUs, even when considering price parity, even when considering the cost. And you can also see that these asymptotes are not don't block you as much anymore because the compute density is, there's so much more compute density. You can do so much more compute with less workers, which means that overhead of communication between all the different workers isn't as impactful. And so, which is why I think like with really large scale problems, GPUs can help in more ways than just be able to go faster. They allow you to just go even do so much more. It's worth noting here that what Thesis is doing here, there's no sorting, there's no indexing, there's no caching, there's nothing like that. So we're not cutting any corners or cheating. This is really just the power of the GPUs and how we're able to harness all the hardware. But when you're working now in a distributed context, you know, as I mentioned, when you go from a CPU world to a GPU world, now you're less likely to be compute bound. When you then go to be distributed, not only do you have to contend with bottlenecks on the storage side, but you also have to contend with bottlenecks on the networking side as well. And you want to, you know, ameliorate those bottlenecks as much as possible to keep the GPUs busy and doing as much work as possible. And that's where you have to start thinking beyond just the technology behind the GPU and also thinking about how these different interconnects work and how networking works and how to make those faster as well. Because the same way that GPUs keep getting faster and faster, more powerful, these interconnect technologies have also been evolving and getting faster and faster, and how you interface with them is also evolving. So if you want to then have these distributed systems being able to continue to be fast and really leverage those GPUs, you also have to pay attention to how you communicate with your storage layer and with your communication layer. Now here you can see NVLink, which is used for communicating between GPUs, and also certain technologies can also communicate with your networking stack, has been getting dramatically faster with the newer and newer generations. And similarly with PCIe, which connects the GPU to the rest of your system, to host and to RAM and to storage. So when you are moving data across these sort of interconnects, there's a couple things that you kind of want to be aware of to really maximize the performance there. So certain types of networking and also certain GPUs allow you to use GPU direct RDMA to communicate with like an InfiniBand or RoCE communication layer. Similarly, on the storage side, there's GPU direct storage. By the way, both of these are NVIDIA, and I apologize, a lot of this whole talk is more NVIDIA centric. But GPU direct storage also allows you to communicate more directly with an NVMe storage layer or NVMe over Fabric, more distributed storage. And if you use those technologies, it is significantly faster because it avoids going through a balance buffer through the CPU, through like the host memory, and it avoids going through the OS kernel. And so it ends up burdening your CPU a lot less. You avoid a copy, and so it's a lot faster. So one of the questions that comes to mind here then is like, okay, how do you then leverage a lot of all this technology? And if you're doing more like distributed GPU computing, what are some of the tools and technologies that are out there? Well, Dask is a very popular Python library for doing more distributed computing, and Dask is more like the scheduler. So if you couple Dask with something like cuDF, then you can use, you know, Dask with GPUs, and you can even configure it with OpenUCX so that you can take advantage of like GPU direct. UCX, by the way, it's a high performance communication library, very popular in the high performance computing. It can kind of help interconnect with like InfiniBand, stuff like that. Spark Rapids is a Rapids or GPU version of Spark. It can also use some of these technologies in certain cases. If you want to go more low level, you can use MPI, which is a message passing interface, very also popular with high performance computing. can also use some of these technologies. Or you can also use Theseus, where more if you're trying to do distributed SQL, very high performance, it will also use these technologies if it's available on the hardware that we're using. Which I kind of want to segue from there, like just to make a special shout out to Theseus and like what we have built there is very much built from an accelerator native perspective, thinking very much about the GPUs and all the different interconnects and how it interconnects to all the different interfaces and all the different tools around there. It's very Arrow-centric, which kind of goes back to what I was saying about Arrow, that allows you to really connect with a lot of the tools out there in a way that's seamless and with as little serialization as possible. And very composable so that we can evolve it over time and adding, because we built it originally with GPUs, but now you can also run it without GPUs. You can use just CPUs as well if you don't have any GPUs. Aside from that, that is the end of my talk. If love to hear any questions.
Thank you, William. Very interesting talk. So I have a few questions from the audience. So one question is that from Discord, and person asking, like, can you go back to the slide on this performance on CPUs flatlining, and why was the performance flatline?
So basically, it's more about from a Spark perspective, like the more workers you add, there's only so much that you can distribute. I mean, if you add more workers, then each worker is doing a little bit smaller part of the problem, but they still all have to intercommunicate to kind of get to the final answer. Especially like in SQL and in a lot of this kind of distributed computing, there are a lot of algorithms that also have effectively what we call like a pipeline breaker, where after all the workers have computed a certain amount of thing, all the workers have to intercommunicate and say like, oh, okay, this is my result. This is my result. They kind of have to all merge. And so the more workers you have, these breakpoints basically halt all progress across all workers until they're all done with that phase or that stage, and to then merge their results before they can continue to the next stage of processing. So that's kind of one of the reasons why it gets to a point that more workers isn't really going to help. I mean, it'll help if you're then doing more data, and then your curve will, you end up with multiple curves if you kind of think about it that way, which is why, looking at like Spark between 10 terabytes and 30 terabytes, the added workers do help, but eventually it'll also plateau.
Thank you.
So hopefully that answers the question.
Yeah, I hope so too. Sorry, I was asking somebody else questions. So I have another question. Is that I find a slide on the guy like, okay, if your workload is latency bound, IO bound, or compute bound, and do different things, but how does one person, how does the users know like what is if their workload is bounded by different aspect?
Really, I feel like and this is kind of like pretty universal when you're trying to figure out your performance characteristics of your software, what it is that you're doing, you have to profile it somehow. And it really is going to depend on what library, what tools, what language it is that you're using, that you're then going to want to go profile things. And so all the possible tools that I feel like it's a little bit outside the scope of this, but if you're, say, for example, if you're doing something only on the GPU, you can do using NVProf or like different profiling tools, you can see how much time your program is spending moving data from a host to GPU, or you can use, if you have, for example, with really large distributed systems, we hook up our servers to some tooling that gather telemetry and send it to Datadog, and we can kind of like monitor and see like how often different parts of execution are taking, whether it's doing disk I/O or CPU compute versus GPU compute, data movement, host memory or GPU memory consumption. And a lot of these things can also kind of help you identify your performance characteristics and where your bottlenecks are.
Thank you. So another question is that, like, when you say about like the columnar format is like better for GPUs, can you explain it why? Like, what is special about the columnar format that make it like easier to work on GPU?
Certainly. So in general, like whenever, especially when you're moving data between hosts and the GPU, you want to move data that is in contiguous buffers. And so moving data that way will always be faster. Not only that, but in a lot of the algorithms that you're doing, you want to have things in nice vectors so that you can be then more easily indexing across the data and then therefore parallelize how the different cores of your GPU are processing different elements of the data in your vectors, which is kind of similar. We saw in one of the talks earlier, a kind of very classic type of code where you have like the different arrays and blocks and dimensions all together creating indices and how they're parallelizing and accessing data across your vector. And so when we talk about like a column of data or in columnar effectively translates to a vector and one contiguous buffer of memory that you can easily index and more easily parallelize across all the different cores.
Thank you. So just another question is just like we got a lot of upvotes on Discord. It's like, what are some of the typical use cases of TCS?
Sure. So Thesis in particular excels at very, very large data sets. So it's not necessarily like there's a specific industry that or type of analysis. It's SQL. And I mean, SQL is one of the most widely used languages for data analytics out there. And so it really depends on like what it is that you're doing. But particular is very useful for people with very large data sets, like hundreds of terabytes. And so, you know, not a lot of companies have that much data, but, you know, companies that particularly have that kind of data and that fits well the sort of capabilities that Thesis has are things like really large retailers, banks or financial technology companies, data security and networking, all these sort of companies that produce a lot of data that have to analyze that data in a way that's fast. I mean, if you think about networking and cybersecurity, you have networking stacks can produce, like from telecoms, can produce, you know, hundreds of terabytes of data every day just from all the different connections and all the IP addresses and everything that they're doing. If you have very powerful, fast analytics, then you can do threat detection and anomaly detection, system, you know, failure detection, all these things which you want to have a very fast turnaround time. And so that's where the power of being able to analyze very large amount of data really quickly is an extremely valuable and powerful tool.
Thank you. Okay, so I think that could be like concluding our workshop today. I'm really glad that we stay on time. Thank you so much, William, for the talk. I want to stop the presentations now on YouTube. Oh, for everyone still watching on YouTube, we have other events in the future from our community. So do check out the events tab or check out my calendar.